Here's section 7.6, where we're looking at potential energy for gravitational and electric forces. Our objectives here are to use the connections between force and potential energy to solve some gravitational problems and problems involving Coulomb's law as well. Now earlier we introduced the concept of gravitational potential energy. That was energy associated with a system of objects interacting through some sort of gravitational force. But remember, we did put a stipulation on using this gravitational potential energy in the way that we initially introduced it. We initially introduced that gravitational potential energy to simply be a mass times a gravity times some sort of change in position or a height. But the stipulation that was on that equation was that objects had to be near the surface of Earth so that that force of gravity was constant. That in fact that force of gravity was still just that mg. And again, that's only true when you are near the surface of Earth. What we want to do in this section is come up with a more general equation that will work for all separation distances, even if you're not close to the surface of the Earth and instead moving pretty far away from it. Now, since gravity depends on a 1 over r squared, or this inverse square law, our equation will likely be more complex than just an mg delta y. Remember, we earlier said that the force from gravity is equal to this negative gmm over r squared, where the r hat is the unit vector from the center of mass of the Earth to the object that we're looking at, and again, the center of mass of that object. And the negative sign indicates that this force is in a downward direction or toward the center of Earth. This equation represents that gravitational force on a mass m above the Earth. So remember, when dealing with these extended bodies or objects, we always want to measure distances from the center of mass. So for example, if we were looking between the Earth and the Sun, we would want to choose the center of mass of the Earth and the center of mass of the Sun and measure our distances that way. So this equation we had already seen in looking for that gravitational force between those masses. Now imagine that you're moving in a gravitational field. Your potential energy is going to change because your position changes. Maybe you start out some distance away from the center of Earth, and then you move further away to some r sub f. Your potential energy is going to change as you move between these two positions. We can find an equation for that potential energy by integrating the force. Remember, we said that for any force, if we knew the function representing that force, we could take the negative integral of that force, and that would give us a function for potential energy. Tacking on that u sub I would give us a initial potential energy. So if we integrate this, we would find that integrating gmm over r squared, or negative gmm over r squared, these negative signs would end up canceling out. And you could pull the gmm outside the integral and really just end up integrating a 1 over r squared, or really just an r to the negative 2. When we integrate that, we would raise the power by 1 and get an r to the negative 1, and then divide by that new power. Now when we look at our limits of integration, we're integrating from an ri to an rf, so we can plug those into our function of 1 over r. Again, the negative sign comes back from dividing by the negative 1, and r to the negative 1 really just becomes a 1 over r. So we can plug in our negative sign, we see that popping up. We can plug in the rf and the ri and subtract those two using the fundamental theorem of calculus, and we get a function that looks like this gmm over an ri. But again, we need to define our reference point for where u sub I is going to be equal to 0, because we do tack on that initial potential energy. Now, a good place to choose for a potential energy equal to 0 would be the point where your force goes to 0. So as we look at, being some distance away from the center of Earth, being here, you don't have a force of 0. You're right on the surface of Earth. You're still some distance away from its center. You still have this gravitational pull. So if you were looking for a place where your force would go to 0, that would be at infinity. At infinity, there would be no more gravitational pull from the center of the planet. So if we choose Ri to then be infinity, the initial potential energy would go to 0. Ri would now become infinity, and 1 over infinity really just goes to a 0. So this entire term would cancel out, and we would simply be left with that potential energy being a negative GMM over r. And this is for separation distances r that are greater than the radius of Earth. So again, we would use this equation when we are very far away from the center of Earth. If we're very close to the surface of Earth, then the mgy would be something that would work, or an mgh would be something that would work. But realistically, as you get further and further away from the center of the planet, your potential energy is going to change, and your function for how you find that potential energy is going to change. It's not simply an mgh anymore, but because the gravitational pull of the Earth changes as you get further away, you see how this function then begins to change for that potential energy as well. Now, although this was derived with a particle and an Earth system, and that's how we sort of described this equation holds for any two particles, M1 and M2. If you have very large objects that are spherically symmetric, you can measure the r distance from the center of the sphere. And this can even be extended to 3 or more particles. If you have 3 objects or planets or stars that are sitting some distance away from each other, you can find the total potential energy as the sum of that potential energy between all the pairs of particles. So find the u between these two, the u between these two, the u between these two. And you can find that total then potential energy as just adding up all of those potential energies there. So what other force do we have that varies with the inverse square of the separation distance? That would be the electrostatic force between 2 point particles or charges, which is defined by Coulomb's law. Remember, Coulomb's law is giving you the force between those two charges as kqq over r squared. So again, an inverse square law looks very much like gravity. We could go about the exact same mathematical analysis for gravity and find an equation for potential energy through integration again. And as we integrate this equation that looks very similar, we would end up with an equation that also looks very similar, where the potential energy between these two charges is equal to a kqq over r. Again, we'd set u sub I equal to 0 at infinity, and the equation ends up looking similar to gravity with one exception. Gravity's equation had a negative sign in front of it, and this one doesn't. And that's because this equation could end up being positive or negative. If we had 2 positive charges or 2 negative charges that we stuck in here, we can see how the overall sign on this equation would come out to be a positive. But if we had one of the charges as a positive and the other one as a negative, we'd see that now our overall equation ends up with a negative sign in front of it. If 2 charges are opposites, they're going to attract each other. And as that distance between those 2 charges, if this was a positive and this one was a negative, as these things get closer and closer together, your potential energy is going to go down or become more negative. All attractive forces have a negative potential energy. And if the charges are opposites, we'll see that that negative sign automatically appears for us. If the 2 charges would be the same charge, they would repel each other, and that would give you a positive potential energy. Let's look at a quick example of actually utilizing this equation and really just use this almost as a bit of a proof, where we're showing that this equation really does simplify down to our familiar expression of mgy. So we have a particle of mass m. It's going to go through a small vertical distance, delta y, near the Earth's surface. And we really want to look at this equation as starting with the more general equation for gravitational potential energy. So that GMM over r. And again, remember that r, we came up with that as looking at the distance or the difference between 1 over rf minus 1 over ri. What we're going to do with this equation, and let me get a different color here really quickly. What we're going to do with this is we're going to give ourselves a common denominator. So this will now become a fraction that we can combine. So when we combine these two terms, we end up with our Ri minus Rf on the top, and our denominator of this common denominator of the Ri being multiplied by the Rf. With this negative sign out here, we can sort of filter that through and get the GMM and filter that negative sign through so that the negative now goes on each of these pieces, or we end up with an RF minus an RI over the common denominator. Now, what I want to point out is that if you are near the surface of Earth and you're going from RF to RI, or RI to RF, you are really just going through that delta Y position. So this piece here essentially just becomes your delta Y. And if you are near the surface of Earth, both RI and RF are just about equal to the radius of Earth itself. If this was the Earth here, and this was the radius of Earth, and you're going from here to here, this tiny little distance that's near the surface of Earth, you're really just close to a radius of the Earth distance away in each position. So really what you have on the bottom of this fraction essentially just becomes a radius of the Earth distance squared. So that one's about the radius of Earth, and this one's about the radius of Earth. So when we simplify this even further, we really end up with just a GMM over the radius of the Earth squared being multiplied by a delta Y. And if you recall, GMM over R squared is really our equation for the force of gravity. And that force of gravity is an mg. So you can see from this quick analysis that utilizing the GMM over R does in fact simplify down to mg delta Y when you're close to the surface of Earth, but the real power of this equation comes in when you come to distances that are much further away from the surface of Earth and are looking at larger bodies like Earth and Moon, Earth and Sun, a couple of stars that are some distance from each other. That's where you really find this equation being used.